We've seen a couple of interesting applications of suffix trees already, namely the standard string matching in the context of text indexing. We pre-process the text. And we've also seen this problem that looked very hard at the beginning and was conjectured to be hard, the longest common substring of several strings. But using the generalized suffix tree, it was actually fairly straightforward to solve that in linear time if we can construct the suffix tree. Now that's not all. You can do even more with suffix trees. And one quick section is on longest common extensions, which is another little threshold concept built on top of suffix trees that makes even more other interesting problems easily solvable. So what is this? It's a little bit abstract. So it's defined as follows. We're given a string, a text, as usual. And the goal is to spend some time on this string, but then have a way to quickly answer LCE queries, longest common extension queries. And those, again, are given 2 positions in the text. And I ask you, how many characters can you continue reading at these 2 positions simultaneously? I mean, continue reading means they match the same characters to the right. So how far can you read the same text at both positions? OK? So it's, well, you can define it formally like that if you want, but I've explained the same concept. Of course, we'll use suffix trees, but also you might recognize that these longest common extensions are very related to longest common prefixes of suffixes. And, well, indeed, they're the very same thing. So the longest common extension at 2 positions, if this is your text and you're asking to extend to the right from here, so there could be a certain length you can read so that these 2 parts match. So if these are the same, well, that means that the suffix of the text ti and tj share a common prefix, and L is the length of this longest common prefix. So this equality is not surprising. Essentially, the 2 things are the same. They're just using a different name because they come from a different perspective. The longest common extension is something that's only looking at the string. It doesn't talk about suffixes. It doesn't care about suffixes. It only has 2 positions and tries to continue reading there. I'll show you a very nice example of why this is interesting and why it's useful to be able to answer those queries. But bear with me for 1 or 2 more slides. All right, we can do LCEs if we can do LCPs, the longest common prefix of 2 suffixes. We've already talked a little bit about those. Those turned out to be the string depth of internal nodes. Now, previously, we were only interested in finding any of those nodes of maximal string depth, or in the longest common substring problem, any of the deepest nodes that had all the substrings in the leaves beneath it. But we can be a little more precise about exactly what internal node we're interested in. If we have 2 leaves I and j, those are the starting indices of the suffixes. So maybe do an interesting example. Say we take T5 and T1 in our banana ban. So it's a ban and anana ban. Then we can ask for the longest common prefix of these 2. Well, it's easy to check that it's just the single A that matches. Well, easy to check if you can still read it down there. But how can we answer this immediately in the tree without looking at the strings? We take those 2 leaves, and we find the lowest common ancestor. That is the first node where, if I start walking upwards from those leaves towards the root, where I first meet at the same node. I mean, where the paths meet, not, I don't have to time it right so that they can't miss each other. The idea is that this is one path, this is the other path, and they're joined at this node. That's the lowest common ancestor. It's the lowest node in the tree that is on both paths. Okay? So that's exactly this one. And now the statement is the longest common prefix, the length of the longest common prefix of two suffixes is the string depth of the lowest common ancestor of the two leaves corresponding to those suffixes. It's a simple concept in the tree, so keep the picture in mind. In formulas, it's written like this. And to spell it out is it's a little longer than I wish it was. We'll use this idea over and over again, so keep that in mind. If you have the leaves, I'll just say the same thing again. If you have the leaves for two suffixes and you want to find how long can you continue reading from their position, you find the node where their paths join and take the string depth there. That's it. And if you know the path to that node, you also know the longest common prefix that they share. That's not really a new application of suffix trees, isn't it? That's the same thing we've been doing all the time. And also, it leaves open how on earth we should find this lowest common ancestor efficiently. But it sometimes helps to just translate a problem from one language into another, and then suddenly other solutions apply. And that will be true in this case too. So how do we find LCAs, lowest common ancestors? A simple way is to just walk up the tree until you find the same node. That's all right, but it can take a long time if the path is really long. That's almost the best we can do if we don't allow ourselves to look at the tree beforehand. But this is a suffix tree. We already spent quite some time to pre-process the text and build this tree. You might spend some extra time on the tree to pre-process the tree so that we can find LCAs more efficiently. Well, the very boring thing is we could take all the pairs of leaves and pre-compute the lowest common ancestor. That's great. We can do just a table lookup and find it in constant time. But it needs a lot of space and pre-processing time, so that's too much. What we will need is something in between. Store a little less and pre-compute a little less, but still do less work at query time. In this case, I will not show you the actual solution. I will show you the black box. It's possible to get the totally best out of both worlds. You spend linear time on the tree before the game starts. And afterwards, you can do constant time queries given any two leaves. So that's the same query time you would get if you pre-computed all of the pairs, all the big tables. But you do the same pre-processing time you're doing already. You spend linear time on the text. This is not beyond the scope of this course in terms of the complexity. We could well do it, but it's eventually I had to make a cut, so I decided we won't do this. So this will be a black box. You can believe that it works, and there's implementations of this also, but I won't go further on this. So we'll just use it and don't care about what's inside. But I wanted to point out that we're already, so this construction to find longest common extension in constant time in linear pre-processing builds on the suffix tree construction. So you can't get one without the other. I just point this out because you could have the smart idea to use this data structure to quickly construct suffix trees, but that's a circular dependency. That doesn't work. Okay, so the thing to keep in mind is this box. If you're given a tree and linear time for looking at the tree and some space to store some extra information, you can find longest common extension. You can find LCAs in the tree in constant time, and if you apply this on the suffix tree, you can find longest common extensions in strings in constant time for each query. Okay, so that's a pretty mighty tool. You can look at the text once, but then I'll ask you position 5 and 17. How far can I jump at the same stage? And you say immediately 17 steps. Okay. What can we do with this? One application of that is approximate string matching. So just to motivate this a little bit, everything we've done up to now was you're given a pattern and you ask exactly does it occur or not. And well, if you imagine search engines have to deal with whatever you type when you type on phones, so there will be mistakes. It would be useful to also find close matches. Matches in the text that are almost a pattern but not quite. The simplest version of this approximate matching is called k-mismatch matching. And well, we need a little definition for that. The main idea is you allow k positions in the pattern to be wrong. Okay, the setup is we're given the text and the pattern eventually, but we also fix this. We're also given how many mismatches we allow. And then we find a position in the text so that this portion in the text, same length, and the pattern differ at most k positions. Well, I could have asked who of you has heard Hamming distance, but maybe not so many. Can we do hands? Who has heard Hamming distance? Who has not heard Hamming distance? Who can hear me? So Hamming distance is, I think I have a question for that, but I just don't want to use the same example so that I don't spoil this. Let's do an abstract one. Hamming distance compares two strings of the same length. So important part is the strings have to be the same length. And then you look which characters are the same, and some others might not be. And you just count how many characters are different. So positions where the characters in the two strings are different. So this will, okay. This would be Hamming distance 3. Hamming distance 0 means the strings are the same. 1 means you messed up one character, 2, and so on. Okay, easy enough. Very quick question to see if you're still awake. All good? Almost. Okay, I think I'll stop it here then. Okay, the correct result is 2. That's very helpful that it gives you the standard deviation and arithmetic mean of what you typed. Okay. The correct answer is 2 because the H, the first position, is not the same, and the last position is not the same, and the middle 3 positions are the same. Okay. That's the simple concept. Hamming distance just allows same length and then counts how often things don't match. So the easiest way of talking about approximate string matching is to use Hamming distance. So we find all matches that are within Hamming distance k of the pattern. This is almost searching with typos, but you would probably want to allow other types of mistakes, like forgetting a character or, well, inserting one that shouldn't be there, things like that. So the reality is a little more complicated, but the first step is this. Now we use our black box, so we assume we can do this LCE data structure, longest common extensions. And what we do is we take the text and we append the pattern. Now then we compute the longest common extensions on this new text, the longest common extension data structure. For that we will need the generalized suffix tree, and we will have to compute all the string depths in the internal nodes, and then we will have to do the lowest common ancestor data structure from the slide before. That was the black box. Okay, how do we use this to find approximate string matching? Okay, I should have shown this one. How do we find approximate matches with this? It's called the Kangaroo Algorithm because figuratively it checks two positions. It checks each position that could be a match after each other. So for every possible positions I in the text, we check, does the pattern occur here? And the kangaroo comes into the game by jumping over equal parts. And we do this in one step, because the LCE data structure just allows us to do that, exactly that in constant time. The kangaroo always lands on a position where there's a mismatch. Otherwise, it would have jumped further. So we just count this position as a mismatch and go one more to the right with both positions and then jump again. And we jump k times, or well, whatever, k or k minus 1 times, so that we have k mistakes. I guess we jump k plus 1 times. And if we've reached, using these jumps, the end of the pattern with our p, then we actually found an approximate match at this position. Okay? So the algorithm, again, is not very, very complicated. It counts how many mismatches we already had. First of all, it tries all positions in the text after each other. It counts the mismatches that we've accumulated so far, and it keeps track of the position where we are in the text and in the pattern. Then we do one kangaroo jump over the equal part, and we jump over the next position, which is a mismatch. So we count one in the mismatch, and then we keep doing this until we are at the end of the position, the end of the pattern, or we run out of mistake budgets. Why is this better than doing a naive algorithm? What would be the naive solution? You could also take this loop and then check all the m characters individually. That would work as well, but it would give you n times m character comparisons, because you have, for each position, you have to check all the characters in the pattern against the text portion. Now we can do this in O of n times k. If you just compare those two, well, it's just replacing one letter by another. I don't care so much. But the pattern could be fairly long, whereas k typically will be small. Otherwise, it's not really an interesting match. If you allow most characters not to match, then it's unclear how meaningful this is. So say you allow k 2 or 3, then this is still linear, whereas for the long pattern, the brute force method would be substantially slower. So it's clearly efficient for small k and less interesting, as the entire problem is less interesting if k is big. As many times before in this class, here's some more more pointers, much more fancy and advanced methods allow you to improve on this result. But I won't discuss the details of how. So that's the Kangaroo algorithm. That's one application of longest common extensions. You can slightly twist this to do something it's very similar but a slightly different. Matching with wildcards. That's the situation where your pattern is not a given fixed string, but you allow a certain position to take any value. So it's a specific type of wildcard in this sense. The star here means this can take any character can occur here, but a single one. It's not the Unix shell star where that can be expanded to any string. And it's also not the Kleene star that means repetition in regular expressions. So unfortunately, the star is used for different things. But wildcard in the string matching literature means this concept. It can stand for any character. It's a choker. Okay, it's one character, but we don't care which one it is. You can think about how to modify the Kangaroo algorithm to deal with this situation. It's not much different. You can also we can generalize from k mismatches to k edit distance. So that means you can not only change a character to another one, but you can also delete a character or insert one. So that's slightly more general. The generalization, so the algorithm is not quite as simple as the Kangaroo one, so that's why I didn't present it. But once you get this simple version, it triggered a lot of results where you can do more general things. Okay. Just wanted to add that. And then there's a whole book that essentially talks about suffix trees and what other fancy things you can do with them and how that helps in molecular biology to analyze sequences. All right, that's the end of the long list of applications that I want to present. And wasn't I gentle? I only described 6 and not the 20-something. So we've started out with the innocent task of doing pattern matching when the text is fixed and we can spend time on the text. We found a solution in form of the suffix trees, which has at least in terms of the theta classes, the best possible trade-off. It's linear time to construct it, and it takes linear space once it's constructed. And we can use this for finding occurrences of a pattern in the length of the pattern, completely independent from the size of the entire data set. That by itself is remarkable. But it turned out the same solution was also a key ingredient for many other problems. So by finding this one magic ingredient, we suddenly could do a lot of things. The only downside is that these suffix trees are fairly heavy data structures. So it's linear space, theta of n space. But as always, this big O notation is a little dangerous in that it hides all those constants. And it turns out for suffix trees, both in the construction time and in the space, those constants are not quite negligible. They're fairly large overhead. And in particular for the space, we didn't talk about representing tries in a computer, but very briefly, how would you store a trie? In, say, some standard object-oriented programming language. So we might as well pick Java. You have nodes, and they need to have one child for each character in the alphabet. So we could say our symbols are the 128 characters of the ASCII alphabet. We'll talk about ASCII next unit. It's just the standard, well, 128 characters. It includes the Latin characters in upper and lowercase, the numbers, a few punctuation signs, and that's pretty much it. I'm just saying this is not everything you want. Usually in natural language text you want more. But it's already quite a bit. Every node needs to have the possibility to have a child for every one of those possible characters. So how would you do this? Option 1 is an array that allows you to specify each of those characters, and that points to the appropriate child. So if you have a character, you say child of C, and that gives you a pointer to the child. That means you need 128 words of space in each node. That's quite a large constant. But that's the only way to truly get constant time traversal from one node to its child. You could also represent this with a dictionary. So you map a subset of you map the characters to child pointers, and then you use whatever you choose for representing a dictionary, for example, binary search trees. So this is fine. That gets the space a little down. Not by very much, but a bit. But then you don't have constant time access anymore, because at least if the alphabet is growing, you need extra time to search through this binary search tree now. So there's a whole question: how do you represent tries in a typical computer language? And there's trade-offs to be made. Either the time becomes less efficient, or you waste some space. So whatever you choose, you lose on one side. And well, the many pointers add just a lot of extra space. I think I'm spending too much time on this slide already. It just turns out that suffix trees by themselves are a great theoretical concept, but they didn't have as much impact in practice, mainly for these reasons, that they have a fairly large overhead.